In this video, we focus on the physical properties of amines with a special emphasis on their boiling points, melting points, and water solubility. We will work to understand some of the drivers of physical properties so that by the end of this video, we can compare physical properties amongst different amine molecules and also between amines and other types of functional groups such as alcohols and thiols. Let's go ahead now and take a closer look at the types of intermolecular interactions that amines are able to engage in. The reason why we focus on intermolecular interactions, which are the attractive forces between different molecules within a container, is because these intermolecular interactions are going to drive the boiling point, melting point, and water solubility, where when we increase the intermolecular interactions, we will increase the boiling point and melting point of the substance. And when we increase the intermolecular interactions with water, in other words, like dissolves like, we will increase the water solubility. So in other words, when we're thinking about intermolecular interactions in the contexts of water solubility, what we really have to be thinking about is how the molecule will have intermolecular interactions that are similar to water or distinct from water. If the intermolecular interactions are more similar to those of water, then the molecule will be more soluble in water. On the other hand, if the intermolecular interactions are very different than water, the molecule will be insoluble in water. So hydrogen bonding, for example. Hydrogen bonding is the interaction of electronegative atoms with positively polarized atoms, specifically the electronegative atom that is bonded to a hydrogen. So in the case of amines, we have our nitrogen atom directly bonded to a hydrogen, and we have a lone pair of electrons there on that electronegative nitrogen atom. And what happens in a hydrogen bond is a strong intermolecular interaction when we have a second amine molecule come in. I'll put the H there, the N here, and then again our two R groups here and here. What can occur is that there's a strong intermolecular attraction for the negatively polarized nitrogen atom with the corresponding positively polarized hydrogen. That hydrogen here is particularly positively polarized because it's bonded to an electronegative nitrogen atom. So the electrons in this bond that I'm highlighting here aren't evenly shared between the two atoms. Instead, they're disproportionately residing on the nitrogen, making the nitrogen have a negative polarization, and the hydrogen, in turn, having a positive polarization. The situation at the other nitrogen atom right here is that nitrogen is also negatively polarized, and the hydrogen that's bonded to it is positively polarized. And so, as a result, there's a strong attractive force, since opposites attract, for fortunately or unfortunately, however you want to look at it. The hydrogen that's positively polarized will be strongly attracted to the negatively polarized nitrogen. Hydrogen is positively polarized over here, attracted to the negatively polarized nitrogen, and that's what we refer to as our hydrogen bond. It is not a covalent bond, it's not an ionic bond, but it's an example of a strong dipole-dipole interaction of these polarized atoms where the atoms are extremely polarized. And you will notice that we mentioned hydrogen bonding being the interaction of NH groups with other NH groups, or OH groups with other OH groups, or NH groups with OH groups, and vice versa. So when we're looking at hydrogen bonding, certainly hydrogen bonding is a strong driving force of intermolecular interactions of amines because it's stronger than the other types of intermolecular interactions that we could look at, such as standard dipole-dipole interactions or van der Waals forces. So hydrogen bonding is our first consideration when we think about the intermolecular interactions that amines can engage in. There is one caveat here that we need to keep in mind, and that is the diagram I've shown illustrates that we need a hydrogen atom bonded to the nitrogen in order for amines to hydrogen bond with other amines. So, therefore, we can only observe hydrogen bonding amongst amine molecules for primary and secondary amines. We can't observe hydrogen bonding amongst tertiary amines because remember that tertiary amines have the nitrogen directly bonded to 3 carbon atoms. So in a tertiary amine, there is no place for a hydrogen bond to go because there are no electronegative nitrogen atoms bonded to a hydrogen. So since there's no NH, there can be no H bonding with other amine molecules. And so as a result, when we think about primary and secondary amines relative to tertiary amines, Tertiary amines, if they are otherwise similar, meaning have a similar molecular weight and similar number of carbons, are generally going to have lower melting points and lower boiling points because of the fact that there isn't that strong hydrogen bonding able to occur. What's instead tertiary amines have to rely on is van der Waals forces. Van der Waals forces are also present in primary and secondary amines, but they're dominant in tertiary amines because tertiary amines don't have the option of engaging in hydrogen bonding. And remember that these van der Waals forces, also known as London dispersion forces, are the attraction of nonpolar groups for one another. So when we were talking previously in earlier videos about carbon chains, such as this, which would occur as a long carbon chain and fats and other molecules, that the attraction that these have for one another is due to the fact that there is an attractive force between the carbon and hydrogen atoms along this chain here, and that's what we refer to as the London dispersion force or the van der Waals force. And I'm going to put some little dots in here to indicate the attraction, but that attraction is weaker than a hydrogen bond. So in other words, if an electronegative atom, namely oxygen bonded to hydrogen and or nitrogen bonded to hydrogen, is present in the molecule, hydrogen bonding is going to be the dominant force in driving the types of intermolecular interactions and hence driving the boiling point and melting point up with increased hydrogen bonding. And also hydrogen bonding is going to increase the water solubility because water engages in hydrogen bonding. And so therefore, if a structure can engage in hydrogen bonding, that's going to increase its water solubility. Now let's think about comparing the physical properties of amines with those of alcohols and thiols. We can check off some boxes here to consider what types of intermolecular interactions each of these are able to engage in. We just saw that primary and secondary amines on this chart are able to engage in both hydrogen bonding, so I'll put a check mark there, and van der Waals forces. Alcohols likewise have hydrogen bonding as their primary intermolecular interaction. Van der Waals forces as well. Thiols, on the other hand, are incapable of hydrogen bonding because of the fact that the bond between sulfur and hydrogen is not as strongly polarized as an OH or NH. Thiols, like most molecules, are able to engage in van der Waals forces. So when we are looking at structures and thinking about whether they are going to boil at a higher or lower point than others, we can compare across these functional groups. Let's take a look at an example. So comparing these three molecules, all of which have an isopropyl group bonded to our nitrogen, sulfur, or oxygen, we ask ourselves which of these has the highest melting point and which one has the lowest melting point. In comparing melting points, remember the rule that as we increase the intermolecular interactions, we are going to increase the melting point and as well the boiling point of the molecule. So we have to ask ourselves which of these has the strongest intermolecular interactions. That is the key to solving this problem. In the case of our thiol molecule, that SH group is not able to hydrogen bond, as we saw up here. Hydrogen bonding is a very strong intermolecular interaction. So of the three, sulfur, or the thiol, is going to have the lowest melting point. And if we're looking at boiling point, it would be true that we have the lowest boiling point as well. It is also of these three going to have the worst water solubility because it is the least like water since it can't hydrogen bond. Now comparing our amine to our alcohol, things get a little more complicated because both of these are able to engage in hydrogen bonding. They both have a similar structure with the exception of the alcohol versus amine functional group. So how do we tell those two apart? The rule that you need to keep in mind here is that hydroxy groups, OH groups, engage in stronger hydrogen bonding than amine groups. The reason why alcohol groups engage in stronger hydrogen bonds than amines is because the OH oxygen is a more electronegative atom than a nitrogen, and as a result, it more strongly is able to polarize the bond between O and H relative to the NH bond. And with that stronger polarized bond, stronger hydrogen bonding is able to result stronger intermolecular interactions. And therefore, of these three, the alcohol is going to have the highest melting point and boiling point of the group, and the amine will be in the middle of the road there for melting point and boiling point. To follow up, looking at water solubility, we would anticipate that the alcohol will be most water soluble because it is most water-like. It's strongly hydrogen bonds, just as water is a notoriously strong hydrogen bonder as well. Then our thiol would be the least water soluble because of the fact that it is the only one of these three molecules that is not able to hydrogen bond. Keeping in mind like dissolves like, the thiol is the least like water. Let's take a look at one more example problem where we're asked to determine which of the following has the lowest boiling point. In order to determine this, I'm going to draw each of these out, starting with pentan 1-amine. Pentan 1-amine will have a 5-carbon chain, so I'll draw out my 5-carbon chain here. And at position number 1 is where the amine group is located. There are no groups that are prefaced with the letter N, and so therefore this is a primary amine where we have just our 5-carbon chain, and the branch there to the amine is at position 1. Our second entry here is N-methylbutan 1-amine. So I'm going to go ahead and draw out a 4-carbon chain with the nitrogen at one end of that chain since the position is labeled as 1-amine. Drawing that out, we have our 4 carbon atoms here. And now our nitrogen atom is going to be bonded to a methyl group because it's listed there as N-methyl. So that indicates that we have to fill one more spot of this with a methyl group. And then since the nitrogen will always have 3 covalent bonds unless it's reacted with an acid to pick up an extra proton, and we don't see anything about that being the case here, the nitrogen atom has to have 1 hydrogen there in order to fill its complete octet for this, which would be a secondary amine because there's 2 direct bonds between nitrogen and carbon. And then finally, our last entry here is N-dimethylpropan 1-amine. So I'm going to draw a 3-carbon chain with a nitrogen atom at one end, because propan 1-amine is going to be that 3-carbon chain, nitrogen at one end. And at that one end that has the nitrogen, we also need to put 2 methyl groups because it's called an NN-dimethyl, and NN indicates that the methyl groups are both directly bonded to nitrogen. And that leaves us here with no open position to put any hydrogen atoms. So looking at these 3 and thinking about which one has the lowest boiling point within a container, we ask which one has the lowest or the least intermolecular interactions. The one that has the lowest intermolecular interactions is going to have the lowest boiling point. So taking a look at these, option number 3, our tertiary amine, has the lowest intermolecular interactions because it can't hydrogen bond with other amine molecules in the container. Without hydrogen bonding, that is going to make the intermolecular interactions considerably weaker for this than for the other molecules, and hence it is going to have the lowest boiling point of the 3 structures.